Hello, everyone. For coming, let's get started. So it's my great pleasure to have Oliver Schulte here for a talk on reinforcement learning and causal inference. So Oliver is a professor at SFU, not too far from here. And we met, I think, a couple of years ago at SFU UBC AI event where we discussed causal inference. It was on a different topic, and this one is even closer to stuff I work on, so I'm very excited about hearing this talk, so please give him a warm welcome.
Thank you, Matthias, and also Aaron for the invitation and for organizing. I appreciate the opportunity to tell you about my thoughts on reinforcement learning, causal reasoning. Pascal and I have written a fairly biggish paper. I think it's up to 50 pages. And trying to sort out what the relationship is. I thought it was a good topic for CAIDA because reinforcement learning, decision making is close to each other. And at the end of the talk, maybe I will manage to convince you that the C in CAIDA should stand for causality. So. And also, I'm head of the CS department at SFU since September. So this is a nice break. I'm supposed to be writing an academic plan, but I'm having more fun with you guys here. And also, I wanted to take this opportunity to advertise that we have 2 tenure track positions for searching, deadline December 20th. So if you have questions, let me know. I believe Joanna has circulated, but please think of us. We have 2 CS PhD graduates who are successful faculty in our department. Okay, more advertising. So the last 2, I try to come to UBC roughly every year, at least once. And last time I talked about sports analytics. So I just wanted to give a bit of an update what we've been doing there. And for those of you, who haven't seen me work on this before, then this will be advertising. So I've been working on applications of reinforcement learning to sports analytics. And the big picture is that, to me, this Venn diagram that reinforcement learning can solve the problems of sports analytics. So that's an idea I've been developing since 2015. We have an industry collaborator, and they have a huge data set, 1 million events just in 1 season. We have like 5 seasons. So that's one great thing about sports analytics, lots of detailed data. And you can apply reinforcement learning. And this is just one more slide, kind of our most recent work we've been doing. So this is new compared to last time I was here. So generally, we learn a value function for the National Hockey League. So it does something like this. You're watching a game, and it dynamically tracks who's likely to score the next goal. So here we have, for example, the Leafs against the Flyers. And orange would be the Leafs. And you can see the model is saying, okay, they're likely to score a goal here. And here the model is getting excited, and there they score. I see the model getting excited. That's my model. My better model get excited. So we can build this sort of thing. So we've been doing that for a while. But our new thing is distributional RL. So I think if you are interested in distributional RL, which can model the uncertainty in your value function estimates, I think this is a really nice real-world application. We had a NURBS paper on this in 2022, and people who came to my poster, I was joking with them that this is the only application paper at the whole conference. I think it's true. I didn't see any others. Let's put it that way. Yeah, and then the idea is once we, and so now here you're seeing uncertainty bands. I hope you can see that. So this is where the distributional RL comes in. And once we have that, we can rank players. So we can say, for example, if you're taking an action and you're pushing up your value, your expected value, then you get rewarded. So we can produce player rankings. And then the most recent paper we did actually is, once we have the distribution RL, we can talk about the risk inherent in an action. So for example, you can measure the standard deviation of every action. And then you can talk about players and teams taking risks. And so our most recent result is that stronger teams take more risks. It's a very high correlation, like 0.83 between team final standing and risk taking. Anyway, I think it's all very exciting. Okay, next time I come to UBC, I will talk about that. It's just a bit of advertising. Yeah, but mainly if you like distributional RL, this is a cool setting. Okay, so now I'm going to wipe the slate clean and start talking about causality. And I just like to kind of give an overview and summarize, and then I go into more details. But the high level intuition that many people have, not just me, is that causality and reinforcement learning should really be naturally, let's say, complements, should really go well together. So what are my goals? So first of all, it's a foundations talk. So no experiments, no data, just definitions and theorems. And the main question I want to answer is when and how can causal models actually help RL? So in the end, I have what I think is a clear and fairly simple answer. So I basically need to explain it. And my second goal is to kind of have a tutorial where just to help the communities connect, right? Because the RL researchers say, oh, I don't know, there's all this terminology, and truncated models, and causal effects, and abduction on the causality side. And causality people say, I don't know, there's online, offline. So I'd like to help connect these two. There's also other people who have done this. So Elias Barenboim is a leader in the field, and he's written a long tutorial at various conferences. I think the most recent version is ICML. There's a new one, came out in 2023. Schulte and Bengio and many other excellent people have written a paper on basically causality and machine learning, which also has a section on reinforcement learning. So I can recommend that also for a short introduction. Yeah, so then, so Barenboim and a number of people, mainly at UCI, got a nice NSF grant on the causal foundations for decision making and learning. So that's basically exactly what I want to talk about. I'm excited they got this grant. So when I saw that, I invited myself to their meeting and gave a talk similar to this one, actually. So that's fun. Okay, so what is the common ground? Well, first of all, both fields are interested in the effects of actions. Okay, there's a terminological difference that what we would call action in RL is usually called intervention by, say, Pearl, or treatment, maybe more generally in the causal models and statistics. Another commonality is that time is important for reinforcement learning models. And why is temporal information very useful? So that's well known because of the basic principle that the future cannot cause the past. Right? So if you're asking whether A causes B and you know that A happens before B, then it's be A causing B. So we've got time and we've got actions. What are and so that looks like, yeah, those two fields really should be working together. What are the differences? Well, causality theory really starts with the idea that causation is not correlation. Really basic difference. And what that means, a little more precisely, is that conditional probabilities are different from interventional probabilities, which are also known as causal effects. And so I'm going to define interventional probability, of course, in a bit. As a nice example from Pearl, where he says, well, doctor's visits correlate with illness, right? So you tend to go to the doctor when you're ill, but going to the doctor doesn't make you sick. Okay, so if we want to have a bit of notation for this, so given that you're visiting the doctor, you're likely to be ill, But if I were to send you to the doctor, right? If I were to mandate you to go, because I've mandated you, now there's no more connection between you being ill or not. So Pearl's notation is given that I have intervened to make you visit the doctor, so that's this do visit notation. Really now there's no more connection. Okay, I'll formalize all this later. Okay, so then hopefully everyone says, yeah, okay, causation isn't the same as correlation. But the causality theorist now says to the RL researcher, look, when you're modeling the effects of actions, you should not use conditional probabilities. Because correlation isn't the same as causation, conditional probabilities do not capture interventional probabilities. But RL researchers use conditional probabilities all the time. So me, if I put on my hat as a causality theorist, I just cannot help feeling that's wrong. But the RL researcher, when you say this to them, and I think I have pretty much literally had this conversation with Pascal, who is one of Canada's senior RL experts, says, yeah, okay, I get it. Yes, conditional causation, not correlation. Conditional probability is not the same as interventional probabilities. But what's wrong with the way that I use conditional probabilities? So if I write something like the probability of the next state S prime, given my current state of my action, and I use that to model the effect of acting, and I estimate that from data using conditional frequencies, what's wrong with that? And then they get mad at each other because you're saying you're doing something wrong. So how can we resolve that? Well, so Schulte and Bengio and many others make what I think is an intriguing suggestion. So they say, well, actually, RL sometimes does directly estimate to probabilities. So, for example, in on-policy learning, when you learn conditional probabilities in on-policy learning, you're actually estimating due probabilities for the intervention specified by the policy. Let me maybe just pause here. Can I see show of hands? Who knows what on-policy learning means? I gave a talk at MILA to the reinforcement learning so far, and I thought, okay, I can assume all of RL, but because I put causality in the title, some people came from statistics, which was great. But then during the Q&A, I realized I basically lost all of them with the RL jargon, so I'm going to explain that later. But generally, I'm assuming people are RL. Okay, like for example, to formalize, first of all, they just kind of say this informally, Schulte and Bengio. We can, first goal would be to actually try to formalize what they're saying. So the example I gave, maybe we could prove that the conditional probability of the next state, given the current state, is the same, and the current action is the same as the conditional probability given that I'm intervening to do the action. So if I could prove that, then basically both sides are happy. The RL researcher says, yeah, I can use conditional probabilities, and they're actually interventional probabilities. And the causality theorist says, okay, yes, you're writing conditional probabilities, but really, if you do the analysis properly, you can see that those correlations you're capturing are in fact causal. Okay, so if I could prove this, and so what Schulte and Bengio say here is that, well, basically something like this equality will be true in on-policy learning. But notice that they say, for example, right? They don't say it's only on policy learning. It's actually very carefully crafted, these two sentences. And so one question I want to ask is, well, are there other situations where this kind of equality is true? And then in those situations, actually, RL doesn't really need causal probabilities. But when the identity fails, then RL does need causal probabilities and needs to worry about the distinction. Okay, it's a bit abstract. So here's my answer, and I'm going to explain all the jargon later. But basically, if you're asking when does this equality hold, so if you're doing online RL, then it holds. If you're doing on policy RL, then it also holds. This was Schulte van Bengio's assertion. If you have complete observability, then you still have causation equals correlation. But in this leaf here, you get a difference. So the one RL setting where you get a difference is when you're doing offline, off-policy learning with partial observability. Pascal says we should call it the pool setting. Can't quite bring myself to put that on the slide, but partial, observable, offline, off-policy. I'm just saying that's the end where I'm going. So, but I'd like to, I find I need to spend probably half the talk just explaining all these terms and definitions, and then, you know, I could almost prove everything, almost prove it. So a little bit more. Okay, so that slide is summarizing my conclusion. Want to see a little bit more about how I'm organizing the talk. So if you say something like, well, should reinforcement learning use causal reasoning? As a causality theorist, you can say, well, what kinds of causal reasoning? And Pearl actually distinguishes different levels of causal reasoning according to the complexity. So he calls this the ladder of causation, sometimes called the hierarchy of causation. So the lowest level is association or observation, where you say something like, where you look at conditional probabilities. So my sports example is, how often does a shot lead to a goal, right? And I can just basically count, you know, out of 100 shots, 20 led to a goal. The next level is intervention or action. So if I take a shot, will I score a goal? Maybe I haven't decided yet. So if I'm the coach, for example, and I'm directing you to take a shot, will that lead to a goal? And those two may or may not be the same, right? That's what I was discussing. And the highest level is counterfactual reasoning. So what if I did something other than what I did do? So I failed to score. What if I'd taken a shot instead of making a pass? By the way, I'm just reading a book called A Brief History of Intelligence, where it kind of goes through history of evolution. It says, okay, at this point in evolution, here's the RL concept that, you know, fish and rats and vertebrates are able to do. And the chapter that I'm reading now says that fish can do the interventional reasoning, but not the counterfactual reasoning, but rats can do the counterfactual reasoning. I think that would be a subject of complexity. So the way I designed the talk, I wanted to sort of explain my decision tree, which is at the first two levels, but I also have slides about the counterfactuals. But, you know, it depends on how many questions I get. It's sort of optional, but I do. See, so okay, now I'll do my outline. You can see there's questions already. So first, I'm going to give you the formal semantics of two probabilities, and that's really kind of causality theory 101. But if you haven't seen it, I can give you a nice demo, and that's usually quite revelatory if you haven't seen it. And then we'll go into the RL background. So Elias Berenboim, who I mentioned earlier, was, you know, in co-author, the designed this notion of a confounded MDP. And to study causal inference, I'm going to study problems of causality and especially confounding an MDP. So I'm going to explain what confounded MDPs are. And then that gives me the background that I can show this kind of results, right? That in online RL, conditional probabilities are equal to interventional probabilities. Then if we have time, I'll give you the formal definition of counterfactuals. And the main thing, I'll say this now, and may not have to explain it, but what's interesting is there's a big class of counterfactual probabilities that even in online RL, completely observable RL, they're still different. So if you go to the very top of Pearl's ladder, then RL always does need to distinguish additional probabilities and counterfactual probabilities. That's my claim. Okay, any questions so far? Yeah, I don't mean I lost everyone, or it's all very simple. Either way, it's worth going into the details. So. Okay, so let's look at the interventional probabilities. So do probabilities, this probability of illness given due visit are defined with respect to a causal model. And there's two main types of causal models. You can have a causal Bayesian network or a structural causal model. And the structural causal model is based on functions rather than conditional probabilities. And that's what's needed for counterfactuals. So if we get to counterfactuals, I'll explain that in detail. But for now, I'll work with causal Bayesian networks because they are simpler to define and simpler to visualize. And actually, I'm going to look at a type of causal Bayesian network that Russell and Norwick called a decision network, which, for older AI guys like me, has been known as an influence diagram. And so in an influence diagram, or I should say in a Bayesian network, you have nodes, which represent random variables, and you have edges, which represent, well, if it's a causal Bayesian network, the edges represent causal relationships. So for example, whether or not a player scores causally depends on how close they are to the goal. And if it's an influence diagram, then you have special nodes usually put in a box, which correspond to actions, so the decision nodes. And you have utility nodes or outcome nodes, usually indicated by diamonds. So those are the rewards in RL. One thing that's really nice, to my mind, about influence diagrams is they give you a single causal model for both the policy and the reward. So, if in RL, I guess usually you're used to thinking of those two things as quite separate, but here we put them in the same causal model. So I'm making this simple scenario, deterministic scenario. So the player scores just in case they shoot, they're healthy, and they're close to the goal. Oh, goalie's not, sorry, that's that should be there. Forget about the goalie. Actually, let me go into that. It's not a little bit. So this is the Bayesian network tool from the UBC AI space. Has anyone worked on this? Miguel knows it.
I know it. Yeah.
Have you use it in teaching?
I haven't used it in teaching yet. No.
Okay. I was hoping everyone would be like, yeah. I use that in teaching all the time. I've seen that in all my undergrad classes. So, okay. Well, I love it. So, okay. So here's a Bayesian network. You have the edges, and then you have conditional probabilities. So this is the one that I meant. If the player is healthy and they shoot and they're close to the goal, then the chance of scoring is 50-50. That's what this one is saying. And if any of these conditions fail, then there's no way they're going to score. Okay, so very topic example. And as I mentioned, it also actually encodes the policy. So the policy says if the player is healthy and close to the goal, then they shoot. And if either of those conditions fail, then they don't shoot. And once you define these conditional probabilities and you set up the network, you can do inference. So let's see, for example, if we look at scoring, so the Bayesian network can compute for you that the marginal probability of shooting is 50%. And if we were to make an observation, so if the player is healthy, the chance of scoring goes up to 25%. And if they're close to the goal, it goes up to 50-50. Why? Well, because conditional on them being healthy close to the goal. Well, what's the chance of shooting? 1, right? Okay, let's check that in the tool. Ha! The tool works. You can tell Christina. So, and the other, and David. Anyway, okay, so I love the tool. Thank you all for working on it. It works. Okay, because so they're going to shoot, right? And then the Bayesian network can infer that because they're going to shoot, right? We're in the situation where they have a chance of scoring. Now, one thing that's interesting to note while I have this up, you can reason in the opposite of the causal direction. Okay, so the prior probability of the player being healthy is 50-50, just specify that. Okay, and now if I tell you that their scoring goes up to 1, because the network knows that the only way that they're going to shoot, going to score is if they're healthy. But if you look at it graphically, you've now you've reasoned from effect to cause, right? So there's a correlation that's non-causal, and that's basically the whole difference between conditional probabilities and interventional probabilities comes from this fact that there is this way information flows against the direction of the arrows, or it can flow. Well, it does flow. Okay, so that's a causal Bayesian network. So you can make a model, and you can, in fact, think of it, as I said, as a model of both the domain and the policy. Now, what about the do operator? Okay, so suppose we're now interested in saying, what if I were not to condition on the player doing an action, right, shooting? What if I said, if I were to intervene to make them do the action? So I'll say what the semantics is, and then I'll show you. So you eliminate all the links into the action, okay? And then you set shooting, for example, to be true. So now you have a new model, okay? And then you just evaluate the conditional probability in the new model. So so let's do it. This is a great thing in the UBC tool. I can do it. So I now want to say, what if I were to make the player shoot? Right, so now I'm going to condition on this. I'm going to delete this arrow. I'm going to delete this arrow. Let's see. Oh, well, actually, I guess the easiest. Okay, I'm going to say, I'm going to make this true. Now I have a new model. This is called the truncated model. And now I can ask, what's the probability? Okay, given that they're shooting, given that they're close to the goal. So, now I know they're close to the goal. And they're shooting. Oh, actually, I already said that they're shooting. Okay, so and now in the truncated, in the intervened model, I get a quarter chance of scoring. Okay, if we go back to the non-truncated model, right, so in the non-truncated model, if I say, okay, they're shooting and they're close to the goal, the probability is 50-50. Okay, non-truncated model 50-50, truncated model a quarter. Okay, so why does that happen? Basically, it happens because in the truncated model, when I tell you that the player is shooting, now there's no more of this backwards reasoning. You can no longer infer that the player is healthy, right? Because I've broken the connection between them being healthy and them shooting. Actually, this is like a randomized experiment. Think about it, formalized randomized experiments. This way, you're breaking the connection between the treatment and the properties of the subject. Okay. Anyway, so okay, so if you haven't seen this before, that's probably the most important part of this talk. The formal, right? There is a formal semantics for these interventional probabilities. And that's really what Pearl would say a causal model is. Sometimes people say to me, oh, causality, that's like philosophy, da da da. And what's the definition of causality? And you said there's no such thing as causality in the real world. And, but that's what it is. It's a certain type of query, and you're modeling the effects of actions, right? And you're modeling the situation where, because you're intervening to make the player shoot, and now player health no more has a causal influence. And you get different probabilities. So conditional do probability is not the same as conditional probability. Okay, I wanted to state a lemma here, general lemma, and I'm going to use it later, but I'd like to state it here to emphasize this is purely a fact about the definition I just showed you. So suppose it says the following. So suppose you're observing the parents of a variable, and you're conditioning on the parents of the variable. So then the conditional probability will be equal to the do probability. And intuitively, if we disconnect the parents from the child, the effect of that disconnection, or there is no effect of that disconnection if you're going to condition on the parents anyway. So in my example here, what I'm saying is, if I were to condition on player health, which I wasn't doing in the demo, but if I did condition on player health, then both the trunk. Okay, so here let me also condition on player health just to make this. Okay, now that stays at 50-50. But now in the truncated model, now I get 50-50. Okay, so this is a basic fact. It's very easy to prove with Pearl's do calculus. In the paper, we prove it from scratch, from first principles, just from the definition I gave. Okay, so why is that significant? Well, it says the following. The only way you can actually get a difference in conditional and do probabilities is when you don't observe the causes of an action. And then foreshadowing, what I'm going to say is, well, in which RL settings do you and don't you know what is causing the agent to act? For now, I'll just wanted to say that it's fundamental, right? So if you can observe the causes of the agent's actions, then conditional probabilities will be the same. Okay, so now I'm going to switch to RL, which hopefully will be, see, for most. Okay, confounded NDP. Okay, this you haven't seen. So I just like to have a one-slide kind of summary on these concepts from RL, like on policy, online. So here's a decision problem. I want to drive to UBC from SFU, and I have different routes, and I always take this route, right? In the past, and I've done it like 5 times, so I have some pretty good data, and I can estimate, okay, that's going to take me 55 minutes to route the loop. So you can call that the behavioral policy. Okay, this is the policy that's generated my data. But I'm thinking maybe I could do better if I went down to highway number 1. I'd like to know what would be the number if I were to take this route. Okay, so you can think of that's evaluation policy. It's the one I haven't followed in the past, but I'm thinking about following. And of course, in RL, the whole name of the game is to find the best policy, right? Whether you followed it or not. So this is actually very common, right? We're always thinking about, oh yeah, here's what I've done in the past. What can I do better? Okay, so that's a bit of notation. In this case, I can ask Google Maps, and Google Maps tells me they're actually the same. But the question is, how can I get this number? Okay, so in the on policy setting, these 2 policies are the same. So I evaluate the policy, right, the potential new policy on data that, or I evaluate the policy and data that I generated from the same policy. Okay, so this would be the setting where I'm trying to estimate how long it's going to take me using the big loop. The online setting, the key thing there is that the agent can interact with the environment. Okay, so that's actually my setting. I can take a different route, right? If I have to see every day, take a different route. In offline, I don't get to act. I might observe, right? I might have access to driving logs, right, from other drivers. For example, Google Maps does. Right? But I don't get to experiment. So if no one has ever taken, like, for example, the route down number 1, then I don't have the ability to either do it myself. So that's the offline. Okay. Okay, confounded NDP. Okay, so this Zhang and Elias introduced this in 2016. But people are still working on it. So there was an AI stats paper in 2024. And I'll give you kind of the formal definition and then a picture and then an example. So the idea is that in a confounded MDP, you might have, and typically will have, an unobserved common cause of your current action and the next state. So to formalize that, let's imagine that the state space is partitioned into an observable part and a latent part. And the behavioral policy is executed on the whole state space. So if you're thinking of something like imitation learning, like imagine learning to drive through imitation learning, you've got the expert driver, and the expert driver sees everything. This is actually an example that Barenboim gives. And then the evaluation policy only has access to a subset of the state space. So in this example, he says, oh, maybe all you have is like drone data where the cars are, but you don't see, for example, the taillights. So in a confounded MDP, the setup is that the evaluation policy is based on fewer inputs. So here's my picture. So here you have the data collecting behavioral policy, which sees the whole world, the whole environment, and it passes on only data from a slice. That goes into the learning buffer, and then the evaluation policy will be based on only the part that's observable to the agent. So this confounded MDP, it really raises these questions of distinguishing carefully between different agents, possibly having different perspectives. Okay. And the question is, with this kind of data, with this kind of partially observable data, can I evaluate right, the policy for the that's based on the partially observable data? And in our paper, we say as well, we also want to evaluate the interventional value function, which is based on interventions. And I don't want to go into the whole definition, but basically, you know, whenever you just condition on the action to define the values, you put in a do loop, and we get Bellman equations. But intuitively, you don't condition on actions, you intervene on actions. Okay, so that's abstract. Maybe how does that look in my sports example? So I've got here this scenario, right, where we have the player, so the online view. So imagine you're an athlete, right, and you know whether you're healthy. And here's the offline view. You're watching the athlete, maybe on TV, maybe you're the other team, and you don't know whether they're healthy. It's like their private information. You can see whether they're close to the goal, you can see whether they're shooting, you can see whether they're scoring, but you don't know whether they're healthy. So this is actually exactly the kind of data I get from sport machines. It's in fact my problem. Okay, and I might be interested in now evaluating a policy which now will no longer be based on player health, it will only be based on close to goal. And if you think about the marginal policy, so what I'm observing is that when the players get close to the goal, half the time they shoot. Right, because they don't know whether they're healthy. Right, and I might be thinking, oh, maybe that should be my policy. Right, when I get close to the goal, flip a coin, shoot is probably a half. And how well would I do? So again, just to reinforce that, in the offline view, you actually not see player health. You just see these three variables. And then in this view, when you do this, the conditional probabilities, in this setting, the conditional probabilities and the interventional probabilities are different. So as I said earlier, if you observe player health, right, then you get 50-50. But here, if you don't observe player health, then this was the demo I showed earlier, you have a half. But the interventional probability, right, the true interventional probability is a quarter. So in the partially observable setting, right, this confounded MDP setting, there would be a difference between conditional and probabilities. Okay. And actually, I think this is really a key point. So I wanted to maybe write a lot of text, but just to say it informally. So, you know, just to not confuse anyone with all these equations. And also to emphasize, this is like a real phenomenon. It's not some artifact of, you know, the definition of causality we chose. So imagine that the Vancouver Canucks coach is watching the Edmonton Oilers, and he's like, he sees, oh, when they shoot close to the goal, they get 50%. They score 50% of the time. Just to stick with my example. So he says, hey, this looks really like a promising strategy, right? And he says, okay, guys, whenever you get close to the goal, you should shoot. And then he said, finds, well, when the Canucks do that, they score only 25%. Then he thinks, okay, well, that must just be because my guys outperform theirs. So the question is he right? No. So somebody said, okay. Yeah. Thanks. Actually, thanks for answering. Yeah, exactly. So, but he doesn't realize that the Oilers only shoot when they're healthy. Right, because he doesn't have access to this data. So he's overestimating their true interventional success rate. Okay, so, and I think, so in this setting where you have partial observability, I think this can definitely happen in RL, and you do need to worry about that. Okay, so where does the difference come from? And so then going back to the result I stated earlier, the issue is really whether, now putting this in RL terms, whether the causes of the behavioral agent's decisions are observable by the learning agent. Okay, and we can basically we can prove this. So suppose that the observation signal that the learning agent gets, right, who's executing the evaluation policy, suppose that, it includes the causes of the actions by the behavioral agent. Okay, so if the behavioral agent is giving you data that depend on player health, then this condition says you should also be seeing player health. Okay, and then if you do that, then you can basically show the reward model, state transition model, the value functions. Everything can be done with conditional probabilities. Okay, so let's go through the RL settings. So let's say that the learning and behavioral agents are equivalent if they share the same observation signal. Okay, we have these two different agents. Well, they might be the same, but potentially they're different. And one is the old data is generating data, and O is from policy for the agent that we're trying to learn. And they might have the same inputs, but they may have different policies. Okay, so now when we have the O equals O beta, then we're going to get conditional probabilities, same as the conventional probabilities, causation is going to be equal to correlation. So when does this happen? Well, when we're on policy, then we have that the two policies are the same, so they have the same inputs. So that was the case that Schulte and Bengio. Let's describe it. Okay, so we have recovered their claim, sort of formalized and to some extent proven their claim. Right, all they need is this assumption. In online learning, which they didn't discuss, actually that's the same too, because like let's say if you're doing an epsilon greedy policy, just to choose a very simple example, right, then the learning agent, in order to execute the epsilon greedy policy, needs access to all the observations. Or in the car driving example, right? If let's say you're trying to follow what the expert car driver does, and the expert car driver is based on seeing the tail lights. Well, in order to run their policy, you need to see the tail lights too.
No such thing as online off policy.
There's online off policy. That's what I'm describing, right? You're executing what the expert driver is doing, but you're like maybe the expert driver never turns left, right? And you're saying, well, I'm going to go right. That's my policy. So now I'm off policy evaluation. But I was online because I had the ability to interact with the data. And then the last case is if I have complete observability, so like a Go or chess, right? Now everyone has the same observation signal, right? Everyone's seeing the state of the board. So now also, so if I see you making a move in chess, I would claim that then I know basically that's caused by the board state. So certainly in AlphaGo, we'll treat that as the cause, right? That's the input variable. So now I have observation equivalence, and in all these settings, I don't get the difference between conditional and do. And so the remaining case, the remaining case is the one, right, where I have partial observability offline of policy. Which is also very close to, it's just slightly more general than the confounded MDP. And so another way to look at it is that the confounded MDP setting is sufficient, right, to have a difference between conditional and interventional probabilities. But I'm saying it's also necessary. If you're outside a confounded MDP setting, basically you're going to get you just use conditional. So that's my answer. So I think I'm out of time for counterfactuals, so I can come back for that. So I'll just skip all that. So and they are a bit complex, so it's kind of hard to rush through. Maybe I'll mention one thing. There was a new paper at AAAI where they were using counterfactuals to do data augmentation. So the idea was that let's say if you chose to go left in a certain state and you observed what happened, you could say, okay, what would have happened if I'd gone right? You can run the counterfactual, you can evaluate the counterfactual using the causal model, and then you add that to your data. So it's a kind of rollout, counterfactual rollout. Apparently rats can do this too. Yeah, but it was a recent paper, so I think it's okay. So in our paper, we discuss like a lot of related work, especially through this lens of, okay, when are we doing online, when are we doing offline, when are we doing hybrid setting between online and offline. And we look at these kind of issues, behavioral cloning, didn't mention it, but state abstraction. So, and one thing I think is especially exciting is hybrid settings. So let's say where you have an offline data set and you could do something like learn a causal model and in principle use the model, right, to evaluate counterfactuals, evaluate interventions. But typically there will be questions that you cannot answer in a causal model from offline data alone, for example, about confounders. And so then you could think about doing experiments through your online ability just to kind of fill in the gaps in your causal model. It's a paper by Maxime Gass, whom I actually met at Myla. He was a student there. That kind of goes in that direction. Berenboim in his tutorial emphasizes this quite a bit. You know, I had an exchange with him after I gave my talk and back and forth, and then he is and he was like, okay, there's some details. I can send you my book. If you want, I'm working on a book. I say, sure, I'd like to look at drafts. He sends me this book, 600 pages. And I'm like, okay, that's partly why people in RL don't use causality, right? But also, I believe in all 600 pages, he doesn't talk about this, so which I thought, but he has got great papers on it. So I hope I've gotten you to the point where you can take the 600 pages and you can search for the right keywords. So, yeah, so I mentioned this refinement idea. I think Matthias was talking about Microsoft Research, trying to convince them to use causality. So these guys, actually, most of them are at Microsoft Research, and they have this nice paper, Deep End-to-End Causal Inference, where they start with data, they learn a causal model from the data, and then they run it all the way through. They evaluate how accurate you are at predicting the effects of interventions. I thought it's nice to have everything put together in one paper. We have a paper just on the causal model learning. So from offline data, that's what I mentioned here, and then defining gaps. So I think that's exciting. Okay, so to summarize, so the question I wanted to ask is, in which RL settings are conditional probabilities the same as interventional probabilities? And my answer is, fundamentally, it's about whether the learning agent can observe the causes of the behavioral agent. Of course, will be the same if they're the same, but if you're doing something like learning from an expert, they may not be the same. And then I argue that this condition will be met in online learning and on policy learning, and when you have complete observability. And so then, right, the conditional equals interventional. And then there's these hindsight counterfactuals where you say, well, given what happened, what if I had done something different? There's a quite well-known paper called Hindsight Credit Assignment, pretty well known in RL. Dorna Precock is the senior author that also talks about these kind of counterfactuals. So, And one thing I think is interesting is that these can be different even in the online setting. And in this data augmentation paper I mentioned from AI 2024, that's what they try to leverage. Yeah, and so it's really this setting offline off policy causal. Well, either you go counterfactual or you do the offline off policy causal under partial observability. Yeah, so maybe we should start calling it POO. It's just such a mouthful. You can. Oh, okay, that's a good reminder for me to stop. So that's it.
So I think we have time for questions, whoever is ready.
Yeah, thanks for the talk. Super interesting. I did not entirely understand why about like the observability equivalence on the online setting case. Because I can imagine situations in which you have an expert with like privileged information, but like let's say the student can still interact in the environment, so it will still be an online setting, but that doesn't mean it will be able to like model the world as accurately as the expert because it might not have the same observation.
Okay, that's actually interesting. Yeah. Okay, so it could be you have limited observation set, but you can interact.
Which like just for context, so I come more from like physics-based characters and robotics, and that's like a very common case where like maybe your expert comes from like the simulation, and then you want to learn a policy that eventually you're going to be able to transfer to like a real hardware. So you usually distill information from an expert to a student.
My question would be, how do you simulate the expert? Don't you need, right? How can you simulate an expert if they use information you have?
Yeah, so you would learn like maybe two policies. The expert would have privileged information from the simulator itself, but then the student, you're only going to give it information that will be available in the actual robot as well.
Yeah. Okay, I definitely will think about it. So I think you're saying something like, say in my setting here, right, where I don't see the player health, I might still be able, say, to decide whether I want to shoot or not. So I can be online in that sense. Okay. Thanks. Okay, thank you. That's right. Maybe I did. I don't know. I tried first person versus third person. I don't know. Pascal doesn't like it. It doesn't mean anything.
That was sort of my comment earlier.
Yeah.
It's better. Like this is really beautiful. I love this work. It's like so simple and so obvious in hindsight. The online case, I just completely don't understand how that's going to follow.
Yeah, so like I say, if you are simulating if you're executing the behavioral strategy, right? My argument is to do that, you need to have enough information, right? Enough observations.
But I guess like online doesn't prevent you from manipulating variables.
Yeah, that's right. This is okay. That's the main difference between my setup and the confounded MVP. Yeah. So in the paper, I think you should just talk about these cells. But if you see here, the behavioral policy has no latent variables. So I think that's a little. I mean, it doesn't matter that much for discussing causality, but it's kind of. So I do it. Yeah. So for me, everybody always can have latent variables. But
If I understand the thing correctly, it's that what you're claiming is that data that you generate online is causal.
Yeah.
If you want to learn from it and you're going to use it from the same observations, it's
Yeah.
causal because you did decide to do that action from stuff you could observe.
Yeah.
And I think that's also the same difference. Probably you might have an irreducible gap for the expert policy that knows the state and actually might be online for the when you're playing, but offline for the.
Yeah. Go back to Pascal. So, and I was saying, I saw a talk by Sergey Levine where he talks about first person versus third person, so it must be a thing in our own. That's really what it is, right? If you have the same, yeah. As ideas, I'll think about this too. Yeah.
Great, really enjoyed the talk, really interesting stuff. You have any practical insights as to how much effort one should spend? Okay, so, you use the offline setting simply because the data is available and you'd be dumb not to use it and to bootstrap off of it. And then I guess the remaining decision is, okay, how much online learning should I do to get this extra information to either to build a causal model, which you can then use, I guess, to generate additional data to fill in the gaps in your offline data, or if you thought about that in any in a particular context I guess there's no upper bound on the regret you can have for not truly knowing the causal model versus just running some variables.
Yeah, well, that's really, like I said, I think that's really, I think about that. I like to work on it. There is maybe let's see if I can find a reference later. But so Ehrenbaum and one of his students, I think, so they did something that I think is really one of the most interesting papers I've seen, which is, and it's model free. And basically what they say is there are bounds that basically say, if I, instead of using due probabilities, I use conditional probabilities, how far off can I be? Okay. And then they combine that with, well, I think it's called optimistic exploration in RL, where they say, okay, so at any point I have an interval on my value function, and I'm going to assume that that the true value is at the upper end. So that makes me explore, right? As it's saying, okay, that makes me explore a lot of the space. So that exploration strategy is kind of prior well known, but what's cool is they sort of initialize those intervals, right, with the offline data set using the bounds on that difference. Yeah, I think the bounds come from causal theory and even econometrics. Yeah, I thought it was really cool. And non-obvious. The obvious thing to do, I think, is to do sort of what I would do is to build a causal model, right, and then use that. This is actually model free. I feel like somewhere in the other directions. Oh, thank you. It's called something like dynamic treatment regimes. No, yeah. And I think at least empirically they look at the regrets. Sorry. Yeah, if you want to talk about this more, Michelle, or work on that side. I'm trying to persuade Pascal. Pascal is really, he wants to solve the purely offline of policy evaluation. He says that's what companies want. Yeah. But I'm like, that's really hard.
Yeah, let's go back to the Canuck example for a minute.
Yeah.
Because the data you used for that was when the just saw players within close to the goal shooting their success rate.
Yeah.
But there were players who were close to the goal didn't shoot.
Yeah.
So how does it? So is that the fallacy that's going on here? That's ignored completely? Sorry. Probabilities.
Yeah.
Seems like a base stereotype argument.
Well, I mean, I was making it shorter, right? But when you evaluate, so if the policy, the marginal policy is when you're close to the goal shoot half the time.
But like the story you
Oh,
told.
in the story, let me see, did I get the story? Yeah,
You
that's right.
said when it shoots,
That was
it
determined.
shoots a little bit close, it's not the same as what the ground.
Right,
Because
right.
they were shooting the goal when they didn't score. They're close to the goal, but didn't shoot. So that's being missed, and it seems like Bayes' theorem would get this all fixed up.
It's a good question, but I think, so here I wrote the marginal evaluation policy is actually flip a coin when you're close to the goal. And then in my story, I proposed a different evaluation policy, right, which is legitimate, try to evaluate anything. But I think this one you will still,
What the story is.
I think you. Yeah. Okay, I'll check this. So, but But anyway, why would it be Bayes' theorem? Because I can have the policy that yes, right, is deterministic. Or even if I said 10% of the like, yeah, don't shoot. You're gonna like start mixing two wrong estimates. Is it, if you look, I mentioned this AI stats paper. Oh, okay, sorry, I just found that's a optimal dynamic CML. Oh, but here, but 2020, my CML 2020. That's the paper I mentioned. The mistake exploration. Oh yeah, and then I mentioned the okay. This literature, like the AAAI stats, 2024, there they worry about, even if I only think about the expected values, like not the intervention, right? But basically, they still think I can get that wrong, but it took me a while actually to understand, because I think I had a similar intuition to yours, which is, well, as long as I'm marginalizing, all the expected values should be fine, right? But here they say the problem is that you're neither seeing the behavioral policy nor the
So with the off policy, offline partial observability. How do you think about the do intervention in practice? Is this a question of interpreting the data through the causal model, or is it an actual intervention?
like how can, if you're in this sort of confounded setting, how can you do the do estimate?
I think the question is like, do you want to actually run the intervention, or is it just a way of interpreting the data? To learn something, but maybe not actually do it.
Oh, okay. I think yeah. Or maybe the question is, yeah. So if you could reconstruct the model, right? Like if this is your data, but you can infer the player health, then you could kind of compute the do probability. So if you could infer somehow a perfect causal model with a late variable, you could infer the do probabilities. There's one NERFs paper I cited here where they kind of make that point, except they don't learn the late model, but they just say, okay, they show you the formulas for computing the do probabilities correctly given late model. Yeah, and that's, I don't know, but yeah, I don't know if that's the question. So Pascal and I, like I mentioned, he wants to do the off policy offline. So we're trying that to see, under what conditions can you actually infer
But I guess the goal is always to learn the two probabilities so that you know what policy to use next time.
So once you realize that they can be different, I think it's, yeah, you want the two probability. That's the part where I'm going to causality theorist. That's what you want. Oh, that's it. This is Wang and Wang 2021. There is provably efficient causal reinforcement learning with confounded observational data. That's the one where they.
I just have one last quick question on, this is mainly for discrete action spaces in terms of, do an action, and then, so I'm just wondering how this carries over to continuous action spaces, like how does do actions?
It's still, well, so if we look at the semantics.
It doesn't seem as clean anymore, like that. Like it seems all super clean in the discrete states, discrete actions. Okay, great, super clean. Continuous states, continuous actions. Doesn't get messy. I don't know. It seems to be it's a lot hard. It seems to be it's hard. Well, it's all hard anyhow. But
but you can, when you have your action, you eliminate all the edges into it. I mean, there may be a question if shooting was discrete, like if it was like, I don't know, choosing a velocity at which to shoot. Like, what does it mean to condition or something? Like, what does it mean to, I can't, what's the model of the interaction? Probably I can only, anyway, but I can probably only give you with a fixed precision type of it. Oh, I think that's fine. Okay. And you don't need new conditionals, right? Because the only conditional probability that you'll be changing is for the action, and you're being told the value. Like the only difference between the two models is that this shooting variable no longer, the action variable no longer has any parents.
yeah, but there could be different speeds that you should have. Or
Yeah.
you should, okay, we'll talk afterwards. Great.
That's, I think one of the, and you see, one sees that even more in the, I didn't mention the structural causal model that's function based, because then big models, deep learning. But one of the attractive things in general, and this is also emphasized by Schulte and Bengio, and of course Pearl many times, like when in this intervention model, you kind of make a very local intervention, right? You don't actually change all that much from the model perspective. And so that's something they like to, the graph structure tells you, right? That's okay, this one change there. So it's very, you could say it's very disentangled, maybe not. That's a little. Thank you.